So let's resume what we started seeing yesterday, which was something, as I tried to emphasize, I think it's probably one of the most important arguments in theoretical physics over the past 20 or 30 years, which is an argument by Maldacena in '97, which led to a remarkable duality between a gauge theory and a theory of quantum gravity. And it came from doing some kind of a Gedanken experiment where we think we are someone very far away at infinity, doing some low energy experiment. And the low energy experiment is to prepare a stack of coincident D3 brains and study the dynamics of these D3 brains. And as seen from very far away, we have on the one hand the open strings attached to this brain, drawing this kind of all this possible sum of all these interactions of the open strings with the brain. The lines there are the endpoints of the open strings. The endpoints can be in either of these brains, I, J, so we will automatically get this double line notation and so on that we spoke about. Or we have closed strings flying around at infinity decoupled from the brains, and the two don't talk to each other at low energies because the interactions are irrelevant, and therefore one point of view from someone very far away from the brains to describe the low energy dynamics is to think that we have the effective theory of open strings on this brain, which is n equals 4 super Young-Mills, plus a bunch of closed strings flying far away, which would be 10-dimensional supergravity. But another complementary point of view, instead of thinking from this open string perspective, if we think more from a closed string perspective, rather, if we see time in a different direction, we can ask ourselves instead, what is the background generated by these brains? We go to the string effective action, we find what is the background, and we find that this is a very special background that has two important regions. The region close to the brain, and when we zoomed in and saw what the metric became, we saw this became the geometry of so-called ADS5 times S5, and the faraway region where the geometry becomes flat space. And then we saw that any energy close to this geometry, as seen from very far away, becomes infinitely redshifted and therefore looks like a low energy excitation. And therefore, the idea for this observer at infinity would be that anything that is taking place close to these brains is considered a low energy effect. And because ADS is kind of a gravitational box, we have a decoupling of things going on close to the brain and things going out very far away from the brain. And by looking at the two descriptions, we see that they share the fact that 10-dimensional supergravity is decoupled. We just cross it out, and we conjecture a duality between this 4-dimensional conformal field theory, which is called n equals 4 super Young-Mills. We know some things about it. We know, for example, what is the one-loop spectrum of anomalous dimensions of some set of operators. We derived it in the lectures, right? We mapped it to a spin chain problem and so on. So it's a theory we are already starting to be a bit familiar with. And what would be the theory in 10 dimensions of closed strings in ADS5 times S5, which is called type 2B superstrings in ADS5 times S5. Okay? Any question here? Now, I want to emphasize, of course, this is not a derivation. It's not possible to have such a derivation because this ADS CFT is kind of a conjecture. It's kind of evidence or motivation or arguments in favor of this conjecture. Well, that's what we basically proposed. Because, of course, the kind of regime of validity that you would trust if you would think that you really have control over the picture on the top is when the coupling is small. And the regime of validity where you would really trust what you are doing at the bottom is the regime where strings are classical, so it's the strong coupling regime. It's a bit of a stretch to be able to really have an overlapping domain of validity of the upper and top description, such that upper and lower description, such that you could really infer this duality. But I think it's motivation enough. So now let me just now what's most important once you have a duality? A duality is basically serves as nothing if we don't have a dictionary between things on one side and things on the other side. If I tell you that this theory is dual to this theory, either I give you a set of rules on how to translate a quantity on theory A to a quantity in theory B, or it doesn't help much. Okay? Otherwise, you don't know how to use the duality. So let's just work out a few of the dictionary, not of the dictionary between observables, but just of the parameters at least. So what do we have on the gauge theory? We have the 't Hooft coupling, which is the product of the Young-Mills coupling and the number of colors. Okay? So in this picture coming from string theory, we get a loop every time we attach a closed string to the brain, which when we do a sum over strings weighted by the Euler number of the corresponding surface, we know that this costs a power of the coupling of G string. That's the rules of string theory. Whenever we increase the genus or we add a boundary, we pay a power of G string. So it's clear that the map is such that G string, the string coupling, is the Young-Mills coupling square, which as I will now explain, is related to the radius measured in string units. In this way, but this equal sign is not explained yet. How do we understand times 1 over n, which is the statement that we saw when we were doing this large n analysis, that we expect the string coupling to be related to 1 over n. Right? This was what our end-waving arguments was giving. So what is the string action? The string action is 1 over the string tension, which we parameterize with this 1 over 2 pi alpha prime, right? That you saw. Times, and then you put whatever metric you have, G mu nu, del x mu, del x nu. Now, this metric has dimensions, and in fact, it is given by L square, where L is the radius of the sphere, times the metric of a sphere of unit radius. So we can take out the dimensions outside and write this G as L squared times a dimensionless metric. So this will be dimensionless. We took the dimension, now we measure everything in terms of how many radius of ADS we have, right? So we take out explicitly the L that was appearing in the metric, we take it out, then everything is dimensionless now. So what we see now is that instead of having dimensionful times dimensionful, we can write this, we take this L outside, okay? We use the map between L and the number of branes and G string and so on that we had seen in yesterday's lecture, okay? Remember that there was a map between L and the number of branes because L was related to the source and the source is related to how many branes you put. And when you work it out using yesterday's expression, you see that you get square root of lambda over 2 pi times this now dimensionless metric. Okay, so now this is the metric of a unit sphere times an ADS5 of curvature 1. We took out L explicit, just dimensional analysis. Okay, so now we have a two-dimensional sigma model where everything is dimensionless. And what is in front? Well, this you see is the effective string tension. And you remember that we had anticipated that the string tension ought to be related to the 't Hooft coupling. And we had said that probably we should expect large 't Hooft coupling to correspond to large string tension. Right? This was the regime where strings become classical. And indeed we see, okay, so we see that the string tension is indeed proportional to lambda, not lambda, but it's square root of lambda, but indeed when lambda is large, the string tension is large and the strings become classical. Okay? Okay, so this means that lambda, much smaller than 1, is when n equals 4 is easy, because it corresponds to perturbation theory. And lambda, much bigger than 1, is when string theory is easy, Because it corresponds to classical strings, where the string tension is very large, and we can think of in terms of classical strings. Conversely, lambda very large, n equals 4, of course, is very hard. It's very hard to understand what's going on if we think from the point of view of n equals 4, because we are describing strongly coupled quantum field theory. Right? So this corresponds to strongly coupled quantum field theory. Whereas here, string theory would be very hard at lambda very small. Because it would correspond to highly vibrating strings. Highly quantum vibrating strings. Right? The strings don't have a string tension that is suppressing the vibration, so it's a very quantum string vibrating in space-time. So this is the nature of this duality. It's what's called a weak-strong duality. Like many dualities that we find in condensed matter or in statistical mechanics, this is one more example of a duality which is a weak, strong duality. Easy on one side is mapped to hard on the other side. Hard on one side is mapped to easy on the other side. Okay? And we will see, of course, now you can take it as a very positive or as a negative thing. You can say it's very positive because typically I know very little about very strongly coupled quantum field theories or about very quantum strings. But now I have a window to learn about it. If I trust ADS-CFT, I have a window into the domain of very quantum strings by just studying weakly coupled Feynman diagrams. And I have a window towards learning more about strongly coupled quantum field theory by simply studying classical strings. So from that point of view, you say, oh, this is awesome, this is great. On the other hand, you could say, well, but then how can I check? I compute something on one theory, and I cannot compute on the other because it's a regime which is very hard. So how can I ever tell if this is true or if it's just wishful thinking? Right? So that it has these two different points of view. So on the one hand, it's great if we trust it, but it's terrible if we want to check it. Okay? But okay, this just means that we have to be more powerful, and we have to really raise our bar and say, I really want to check this, so I will have to develop methods in quantum field theory that will allow me not just to study weak coupling, but to go all the way to strong coupling and then check whether this is correct or not. It obliges you to raise the bar and to really aim higher. But a priori, this is why it is a conjecture. This is one of the reasons which is an obstacle towards making it more and more precise. It is just that it relates easy theories and the easy regime to a very hard regime. Now, I wanted to make a few remarks before we move on. So let's start making a few remarks. So first remark. But before, maybe let me ask if there is any question here. Yes?
So is this duality really still like on the level of conjecture? Has nobody really sufficiently proved that it is not actually proved that the duality holds? Or
I will not. I would say it's a conjecture.
Okay,
it's true, but it's a conjecture. Let me make a few comments. I think at the end of the lecture you will see why it is true. But even today you already will start, I hope, believing that it would be a bit crazy if it were not true. But let me make now a few remarks. Okay, there are more questions? Good.
So we said here large lambda corresponds to strings are classical.
Yeah.
I think last time you said that large string tension corresponds to the limit strings become QFT because the strings shrink to a point.
That's an excellent point. Yeah, that's an excellent point that you're making. So now there are yes. So what does it mean if the string tension is very large? It can mean two things. if you fix some kind of boundary conditions, that you say the string needs to end here, right? If you oblige your string to end in some circle, say here, then having a big string tension means that you have just some classical parachutes. And then it vibrates a little bit. Vroom, 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 vroom. However, if you throw strings inside some universe, and you take the string tension to be very large, indeed, they shrink and collapse to points. So now it depends a little bit on what kind of process you are studying. Are you studying some processes which are typically related to big strings or to small strings? If the strings are small, indeed taking the big string tension will mean that you approach a point-like limit, which is a sub-case of these classical strings, where you describe not only where you describe supergravity, where you will have just point-like strings moving in this curved ADS. It's even simpler than classical strings. It is just a bunch of gravitons moving in ADS 5 times S5. But there are also cases where the charges of the string, where the angular momentum of the string is classical and grows with lambda, grows with square root of lambda. That is, you consider a string where the action is finite, where you consider some other charge, J, which is measured in 1 over h bar, which is this quantity here, which is of the same order, which is big, of the same order of square root of lambda. This would be what you would have if you consider a classical rod. So it's always true that it becomes easy, but you are absolutely right that for some quantities, taking the complex to be very large will map you to a even simpler case here, which would be just supergravity, where string theory in this background, basically all these strings inside this background, they shrink to points, and you just have the effective theory of closed strings, which is supergravity. Oh, there. So that's even simpler. We should put an even simpler case. Okay, so good. More questions? But you see that, forget about the subtleties. Naively, we say that we sum over solutions of string. We sum over strings, right? That are moving in space-time. When should I sum over classical solutions only? Well, if the prefactor is very large, saddle point is good. Then the intuition is that I should then sum over surface. But then you could imagine a regime where the surfaces degenerate into geodesics, which is even simpler, like a point-like limit. So that's a further degeneration if the solutions that you are summing over don't have big charges. Yeah? Okay. So the first comment is that we started with a bunch of D3 branes, right? To derive our Gedanken experiment, we decide let's put a bunch of D3 branes and so on. And we could consider something else. We could start with something else. D something else, a stack of D something else, a stack of D something else intersecting another stack of D whatever, and so on. So there are many constructions in string theory that you could take as a beginning starting point, and this will generate other ADS-CFT dualities, other examples. Okay? So it's very easy within string theory to generate new dualities. So there exists many other examples of these ADS-CFT dualities. In fact, more generally, it's not even ADS-CFT, because ADS-CFT means string theory. We see it means the duality. What we expect is always a duality of this flavor, closed versus open. But the background doesn't need to be ADS as you zoom in close to the branes. It could be something else. But it will be a duality between closed strings and open string description. Whether it is really an antecessor or whether it's something else, we should not be. We should have no dogmas. It could be it could be whatever. Yes.
Are we talking about just too many to worry about writing down a classification, or is it?
Yeah, it's way too many. That we will. Yeah. So, having said that, this one is by far the most well studied, and is by far considered the example where we have more control. So there are a few examples. There are many other examples. There are examples, for example, where here you have some simple two-dimensional rational conformal field theories. And then here you have some very complicated string theories of very higher spins and so on. There are many examples. This is probably the example which is more balanced. Neither side is totally trivial, but no side is a monster. Both are reasonable. In fact, if you imagine what's the simplest four-dimensional conformal field theory, it's n equals 4. The simplest conformal field theory you could write. What's the simplest curved background in 10 dimensions? Well, it's a sphere times an hyperboloid. What could be simpler than a sphere? Yeah. So it's probably the most balanced example. Yes?
So you say, I mean, amongst the other examples, you say that it needn't be ADS. I mean, here, because the isometry group of ADS is the conformal group of flat space, I mean, there's at least at zeroth order something that's telling you that there should be something like a CFT on the boundary, but if you have something that has a slightly weirder isometry group, does that affect what happens to the boundary? Is it really still a CFT? Like,
no, it doesn't need to be a CFT. What I said is that there should be a duality between some theory that is governing effectively open strings and one that describes closed strings. There are examples that describe some matrix quantum mechanics being dual to some more complicated curved geometries of some black strings, for example. There are many. There are several examples, and the logic would still go along the same lines. Consider an observer, take a low energy limit, consider a decoupling argument, and so on and so forth. Now, the second comment is that, of course, the sphere S5, if we want, we can Kaluza-Klein reduce. Right? I can always decompose my fields into harmonics of the sphere and replace the field by saying that I just have ADS, but with an infinite number of fields, one per each harmonic of the sphere. Right? This is the usual thing. And I have a compact space. I can trade it by having some infinitely many spins on the non-compact spacetime. ADS5, not really. So in essence, this duality, that's why people typically think of these dualities as being dualities between anti-de Sitter space in D+1 dimensions and CFTs in D dimensions. This is typically what people write. We have a CFT in D dimension is dual to ADS in D+1 dimensions. We see here we also have a sphere, but I want to say that conceptually the sphere doesn't play such a huge role from this point of view. So this is what people say, because of this D versus D+1, that this is an holographic duality. Right? Where volumes in gravity are kind of encoded in surfaces in the gauge theory. Where we have one higher dimension in gravity, but things, it's as if things inside some volume, what matters is the surface of that volume. Okay? Now, indeed, for example, there were hints that gravity should somehow have some kind of holographic flavor to it. So let me remind you of something simple. The entropy of a black hole is the area over 4. Right? The entropy of a black hole is proportional to the area. And indeed, this leads to the idea, that the maximum entropy that you should have in a region, in a given region, should be A over 4. Why? Because suppose it was bigger than A over 4. Suppose you have some regions in this room, the entropy is bigger than A over 4. So keep throwing things inside. Then the entropy keeps increasing. But then at some point you form a black hole. And it becomes A over 4. So if you started with something bigger than A over 4, by increasing the entropy, that is by throwing things inside, you could form a black hole and get to A over 4. But then the entropy would go up, and then decrease, which is impossible by the second law. Therefore, A over 4 should be the maximum. Right? So otherwise, we could decrease it by forming black holes. right? We start inside a room, we throw things inside, we form a black hole, and the entropy would decrease. And this is kind of hinting that the information in a given volume is actually captured in the area, in the boundary of that given volume. And this was what Susskind and others called the holographic principle. That whatever we will have as a description of quantum gravity, it better be some kind of holographic description, these people were saying. We should look for a description of quantum gravity that should be super non-trivial. It should have this holographic nature. That something in the volume should be encoded in something of the surface of that volume. And it was very hard to come up. How could this ever be made precise? How could we ever come up with such theory where things in volumes are actually captured purely in the area of these volumes and so on? It sounded totally crazy. But this is precisely what ADS-CFT does. ADS-CFT gives you a very precise, sharp map. It tells you, indeed, supergravity, indeed, gravity in ADS 5 times S5 is given by a theory in the boundary of this space-time only, which is one dimension lower and which is just simply n equals 4 super Young-Mills. So ADS-CFT is a precise, is a sharp realization of all the ideas of the holographic principle, Which was a principle that was around for a long time. People were thinking about these ideas. What should be quantum gravity? We throw things inside. There is just the area. What is the fact that we are getting just the area and not the volume of the black hole telling us? It's telling us that the information is kind of encoded just at the boundary. So what could the description of how could we ever find a description of quantum gravity where bulk is only encoded in a surface and so on? And all these ideas were kind of floating around, and now we see that it's cute because we see the CFT realizes it very, very precisely. In fact, related to this point, it would be kind of terrible if the duality was not holographic. Because there exists a theorem, in fact, by Weinberg and Witten, that basically tells you that if you have a theory with a Lorentz invariant, let me see more precisely what are the statements. The idea is that if you have a quantum field theory with a Poincare invariant stress tensor, so the theory states that if you have a quantum field theory with Poincare invariant stress tensor with some non-trivial momentum, so the idea is that such quantum field theory forbids fields of spin greater than 1. Basically, what Weinberg and Witten show is that if you try to construct such fields, the expectation value on the Fock space of such fields of the stress tensor will have very pathological properties. And therefore, they say that these theories, you could not have these fields of spin J emerging. So let me tell you what the physical meaning of this, what's the physical statement of this theorem. The physical statement is the following. You could imagine the following. Let's imagine that I have a theory which has gluons. So I put a theory and I put two kinds of gluons. And then I start putting some interactions between my two gluons. I couple them to some matter and so on. And then I ask the question, can it be that these gluons, for example, form some kind of bound states of two gluons with two indices, and that this bound state behaves like a particle of spin 2? Right? Can it be that gravity is some kind of bound state of two gluons? Right? Something crazy like that. You take some two spin 1s, could you ask? And these theorems tell me no, it's not possible. Such states, as you would consider expectation value of T mu nu, would give you some bad stuff. Now note that gravity avoids this, because for gravity, of course, the stress energy tensor of gravity by definition is 0, right? So for gravity, we are safe. But if we have a quantum field theory, like n equals 4 super Young Mills and so on, this seems to be a problem, because we are saying that in n equals 4 super Young Mills, out of the gluons and the fields and so on, we cannot produce something that looks like a graviton. But we are saying that we can. We are saying that we have a duality between n equals 4 super Young Mills and gravitons that are describing in these closed strings. So where is the loophole? What's the problem? Well, the problem is that the assumption of this theorem is that the gravitons move in the same space-time as the gauge theory. But this is not what we are seeing. We are seeing that out of gluons in 4 dimensions, we produce gravitons in 5 dimensions. And this, there is no way this theorem could forbid that. Okay? So the point is that when we were drawing all these Feynman diagrams and saying that we expect gauge theories to become string theories, just by looking at the Feynman diagrams, you don't have the right to say in which space-time these strings are moving. You see, if you draw this picture of the cylinder, right, with many, many diagrams going, you know where are the endpoints of the string. They are at 2 points in space-time. But you have no idea what's the effective geometry felt by this string as it is propagating. Just from these cartoons, you cannot say this string moves in a flat background. How do you know? You have no idea. And in fact, it better be that if we could make it precise, it better not live in the same space-time as the original theory. Because if it did, it could not be, it would violate this important theorem. Okay? So this holography is a way of making it possible to realize this duality between gauge theories and gravity without violating basic principles of quantum field theory. Okay? So again, the assumption here, the main assumption, which we are violating, is the statement that the graviton that we generate lives in the same space-time as the gluons. But we know it does not. So now let's try to think a little bit. So suppose I forget about everything I said, and I just say that I know that n equals 4 super Young Mills in 4 dimensions should be described by a string theory. Because we have nice cartoons, nice pictures. Of course, it was not a mathematical argument, but we said there should be a string theory. So now how could we have arrived at this precise duality? Then we want to see what could be the background, what could be the string theory. So the first thing we know, it is not string theory in 4 dimensions. In fact, string theory in 4 dimensions is not even very friendly. String theory is like 10 dimensions. But okay, 4 dimensions, it's not for sure. It cannot be the same space-time because we know there is this theorem here. So what could be the nature of space-time if we were to guess what it is? We know the answer. It's AdS5 times S5. But let's forget the answer and try to argue how could we have argued and arrived at this answer. Well, that's my one more comment. So we have, in the boundary, we have a CFT. A CFT, which has no scale, so it has a symmetry, and there is scaling, for example, all points. Right? And just rescale, and this is the symmetry of my conformal field theory. Right? The theory without any scale. Now, indeed, if I think of my space-time as dx mu, it does not have this symmetry. It transforms. But here is a very simple modification how we could, just by adding one more dimension, create a space-time that has this particular transformation as an isometry of the space-time. What is the simplest possible thing? You say, let me divide by a z square, where z also rescales such that it's invariant. And I just add this extra coordinate with an extra line element. And this will be the simplest possible space-time that promotes this symmetry of the boundary into some isometry of my space-time. Okay? Right? But this space-time is nothing but ADS5. Okay? So this is ADS5. And to see it, take the metric that we wrote the other day, which does not look like this, and define R to be L square over Z. Then if we put some L square in front to make it have the right dimensions, you will see that this is just the same as ADS5. Okay? So if you take the metric that we wrote the other day, if you take R, go to 1 over Z, you see this is nothing but this metric here. Okay? But then we would say, what is this all there is? No. For example, in n equals 4, we had 6 scalars. And correspondingly, an SO6 symmetry that rotates all the scalars among themselves. Where is this SO6 symmetry in this ADS5 spacetime? There is not. There is no rotation. What is the simplest space that has SO6 symmetry? It's a ball. Simplest. It's the space with SO6 symmetry. Okay. So this is also the symmetry of a 5-sphere. A sphere is the set of points x squared equals 1, which is invariant under SO6 symmetry. But this is great because S5 plus ADS5 gives 10 dimensions. So the most natural background, so the most natural guess would be to say that we have strings in ADS5 times S5. This would be correct. In fact, you could go further and you could say, I know what is string theory in ADS5 times S5. If you reverse the arrows, it becomes almost a derivation, in fact, because you know what are the symmetries of string theory in ADS5 times S5. It's a superstring, you can write all its symmetries. Then you can ask, if I think of the most general symmetry transformations, and I see what it implies for the fields close to the boundary, close to Z equals 0, which is R equal infinity, which is where we approach Minkowski space. Those symmetries should be the symmetries of whatever dual theory I have. And you find that your dual theory should have n equals 4 supersymmetry. So it should be a theory in 4 dimensions with n equals 4 supersymmetry. But there's only one theory in 4 dimensions with n equals 4 supersymmetry. Therefore, they must be dual. Now, why isn't this a sharp, a rigorous derivation? Because strictly speaking, no one knows very well how to define string theory at the quantum level. And this is more kind of a classical analysis that I just did in my mind. And no one knows very well how to quantize string theories in curved backgrounds, and in particular how to quantize the string theory. So it is not, again, a spotless derivation. But you see, we already have 2 more or less reasonable derivations. Very different ones pointing towards the same result. And this is more or less always the status of these ADS-CFT dualities. There's never a very sharp derivation, but there are often many more or less derivations from many, many directions pointing towards the same thing. And for physicists, that's the main distinction between physicists and mathematicians, this is good. For physicists, we accept as value having many reasonable derivations of the same thing, even if they are not very good, we don't mind. We often prefer to have many reasonable derivations than one very sharp one that is very tough to follow. Whereas mathematicians, if they have one good one, they would not care about another one. Why? Sometimes. Depends also. Okay? Now, in fact, this picture here of thinking in ADS in this way is kind of nice. Because what we have is the following. We think of ADS as having some direction z, and this here, z equals 0, was before r equal infinity. And here, up here, z equal infinity was before r equal to 0. And then at each fixed z, we have a copy of Minkowski space. So we think of this kind of thing as kind of a foliation of a space-time with many Minkowski spaces that are becoming smaller and smaller as we go inside. And we have this foliation with several copy of Minkowski space. And then you ask, what could be the interpretation of these several copies? Is there a way of thinking of these several copies from a field theory point of view? And the way people often think about these copies is by thinking that this extra dimension, this extra dimension, it's often possible to think as corresponding to a renormalization group direction. What I mean is the following. If you consider here, at the boundary of your spacetime, 2 points that are close, so this would be some UV process, and if you consider 2 points that are close at the boundary of this spacetime, remember this is equals 0, which was r equal infinity, this is the boundary of the spacetime, and if you see this would correspond, this would be described by some processes that happen at some z small. But if you consider points that are very separated and study what happens, for a signal to propagate, it would propagate inside and so on, and it would go up to some z large. Okay? So short distances in the boundary probe a small z inside, large distances probe a large z inside. So the idea would be that the different copies are keeping track of the physics that at the boundary is taking place at different distances. Longer distances are probing the inner regions of this ADS, and the smallest distances are probing the boundary region of this de Sitter space. And what some people try to make precise is to say, let me start with my field theory, and think of my field theory, introduce some renormalization scale, introduce some RG parameter that tells me how much I integrated. So if I just want to study very infrared properties, I integrate out a lot. And you consider then, you try to see if it could be that this duality could emerge by studying the renormalization group flow of your field theory at the boundary. So people like, for example, Sung-Sik Lee and so on are trying to make this very sharp and precise and trying to see if we can make a sharp connection and understand these dualities as emerging naturally from the field theory by studying its RG flow. More comments. We have our boundary of our theory at z equals to 0. And what we will do is consider inserting some probes at some points at the boundary and then letting them interact. So they go and they interact in the middle and so on. So by this picture, I mean that I prepare some strings with some boundary conditions at 3 points, throw them inside, letting them interact, and see what the final result is. Okay? And what we could do is take this picture and let this define what I mean by a correlation function at the point x1, at the point x2, and at the point x3. Right? I take a theory of ADS space, and I define. And then I ask myself, would this definition, if I take this definition, would it obey all the right axioms that a conformal field theory should obey? Would it have the right symmetries and so on? And the claim is that because the bulk has the right isometries, automatically whatever you will get here will obey the right axioms of a four-dimensional, of a D plus one-dimensional conformal field theory. Okay? So whatever would come out would be consistent with any axioms you would write of conformal field theory. For example, in the conformal field theory course that many of you did not do, but let me tell you what we did, which is a simple exercise that you can go and watch. We did the following exercise. We said, let's consider an ADS-CFT toy model. And what was the toy model? Let me remind you, or tell some of you. The toy model was the following. Take this anti-de Sitter space-time, just this space-time here. Okay? Forget now about the precise ADS-CFT like what we have, and let's consider the following ADS-CFT toy model. And what we did was the following exercise just for fun. We took this ADS space and we considered, we threw geodesics. And we let the geodesics meet at a given point. Okay? So these were geodesics. Okay? And then we said, compute these geodesics, find a point here in the bulk, which has some position x and some height z. Let the weight of this configuration be given by exponential of minus action, which will be exponential of minus the mass of the first particle times this length L1, minus the mass of the second particle times M2, minus the mass of the first particle times L3, and find the minimum of this, which would be find what is the optimal point that minimizes this. So this will be a toy model for this ADS-CFT if we consider inputting 3 heavy sources that propagate classicals and just follow geodesics. And they just move, just minimize, and they look for the best, the configuration that minimizes this. And what did we see when we did it? We saw that this was giving a 3-point function with the right properties to be a 3-point function of a conformal field theory. Namely, it was giving something like 1 over the distance between x1 and x2 with some exponents, delta 1 plus delta 2 minus delta 3, and 2 more factors like this. And you can do it also for 2-point functions, and it also works. 3-point function is more non-trivial because you have to minimize and so on. So as I told you in that example, we could have used this kind of toy model. So this would be a toy example. Where we can sometimes take some toy example, take some ADS space. It doesn't need to be exactly string theory in ADS 5 times S 5. It can be some ADS-inspired example. And use that to define the conformal field theory and see what it would give you, what properties it would give, and so on. Or we could do the opposite. We could use the conformal field theory, take a conformal field theory, and postulate and see, and use it to define my theory of quantum gravity in the bulk. I could say, oh, you don't know very well how to quantize strings in ADS 5 times S 5, doesn't matter. N equals 4 super Young Mills is very well defined. Use that, and use that to define your strings in ADS 5 times S 5. That's another kind of use we can give to ADS CFT. So let me summarize a little bit these comments. Today I think we are almost done. And say that then from this point of view, I think there are at least 3 different ways we can look at ADS CFT. There are at least three natural arrows we can write. now we are talking about more generally the SCFTs, dualities between theories in ADS and theories at the boundary and theories at the bulk. Okay? One way is to take these theories as a definition of the gauge theory. So we take some theory in ADS and we say this defines, by studying what happened as I approach the boundary, it defines my gauge theory. This is, for example, what the point of view of people followed when they study, for example, applied ADS condensed matter, for example. When they take some phenomenological example of some fields moving in some curved space-time, and they say, let this be dual to some graphene or to some superconductor or whatever, it's some phenomenological models. It's never something very sharp. You just put some geometry in ADS5 times S5, put a bunch of fields there. Let this define some holographic condensed matter material, and let me now study response of this material, properties of this material, see what I get. I don't know very well what the gauge theory is when I do this. It's the kind of phenomenological approach. But what I expect in my mind is that given everything we said, this should be describing some strongly coupled field theory. So if I put kind of the right ingredients, the right variables, the right fields, I expect this to capture, at least qualitatively, some nature of some strongly coupled system, like a strongly coupled superconductor, a strongly coupled metal, a strongly coupled something, if I prepare properly my experiment. One sec. So this is what people do when they use ADS-CFT to study ADS condensed matter examples, when they study ADS RIC, where this is quark gluon plasma, for example, trying to study some models of quark gluon plasmas, more phenomenological approaches. More recently, for example, entanglement entropy, using approaches from ADS, which are now very popular, of trying to understand how to understand entanglement entropy of strongly coupled field theories by studying some minimal surfaces in antecedent and so on. These are typically examples where we make some general claims. Let's take some ADS theory. There exists some quantum theory. I'm basically defining it through whatever I will get in ADS, and I'm going to study what are the consequences, what do I learn about strongly coupled gauge theories. Okay? Yes?
What kind of condensed matter models have been studied by this machine?
Oh, I can refer you to some review you can study. You can read off the introduction. Many people typically study.
A coupled limit. You can't get.
No, it's a very strongly coupled limit, and I think it's important to state that, strictly speaking, you have no clue what you are describing. I mean, you have very little clue what material could it be that you are realistically describing. You just say, let me consider putting some ADS4 space if I want to describe a three-dimensional material. If I have some electric field, I will put some gauge field in the bulk that will couple to some electric current at the boundary. I'll try a little bit to put the kind of fields that would couple to the right sources at the boundary and see what I get when I start studying equations of motion of my fields in the bulk. Okay? This is something that was extremely popular a few years ago. Now it's becoming a bit less popular, but some people still are thinking about this kind of thing. Another point of view would be to take this as a definition of quantum gravity. After all, quantum gravity is what, in principle, it's much harder to understand. So we could use this to understand quantum gravity. This has important implications, for example, for the black hole information paradox, for example. If we say that whatever we do as some description in the dual CFT, which is a unitary theory, it might be very complicated, but we know there can be no information paradox. Whatever evolution is being described at the boundary, it must be unitary. So this is kind of important. So if we can use this as a definition of quantum gravity, we can look for conformal field theories with potential to describe real gravity. To describe gravity. Because not any CFT can be a good candidate. I cannot just take the CFT of the Ising model and say perhaps this describes gravity. In fact, there are a couple of criteria that people like João Penedones and others have been studying to understand what could be what could be the good space of conformal field theories that I could use as a definition of gravity? Let me give you an example. What do we want? We want to have a CFT, and the energies, the dimensions of the CFTs are related to the masses of my excitations in the gravity side. So what do I want? I don't want to find on my gravity side a gazillion particles with zero mass, because they are not observed in nature. Only gravitons are. So what I want is to have a CFT which has a funny property, which is that if I look at a spectrum of my operators, a few operators remain with small dimension, but some operators, the dimension starts growing and decouples. So for example, we started studying the dimension of these quantum spin chains in n=4. We saw that we start with ferromagnetic states, and then the dimensions are go up a little bit. They are a bit bigger than ferromagnetic. That's still perturbation theory. Then you could ask, what's the fate of these energies as I continue increasing lambda further? Right? They start increasing linearly. What happens to them? And the answer is they go to infinity as lambda goes to infinity. And this is crucial, because this is telling you that all these states are becoming very massive, and only a few ones, very special ones, would remain massless. And this is why, indeed, you have a potential at strong coupling of having a few massless states, like gravitons and gravitinos and so on, but most states decouple and they become very heavy. And if you give me a general conformal field theory, it's very hard to find conformal field theory with a parametric decoupling of this sort. But you could forget and just see, let me go to the axioms of conformal field theories, and let me say, what do I know if I very abstractly try to look for conformal field theories with the right properties? Let's say, let curly C be a CFT with this decoupling, blah, 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 blah. And I could try to follow an axiomatic approach and try to see what could I learn about quantum gravity by studying something which is under much bigger control, which is the space of conformal field theories. And the third perspective on this duality is kind of a hint provider. Let me explain what I mean by this. Or if you want, a guide. Okay. I can say, well, at the end of the day, I want to learn how to solve this theory. Or I want to learn how to solve this theory. I want to forget about ADS-CFT and just sit and solve this. Or sit and solve this. Then I will check they are equal, because I will solve them. But I want to solve them. Now, this is very tough. So what can ADS-CFT tell you? It's a bit like when you have an exam and you have a question, derive the conductivity or show that the conductivity is equal to blah. The second type of question is much easier. When you already have the result and you just have show that something, right? So this is the same thing. I can use ADS-CFT, and this theory predicts what the behavior of this theory should be in the hard regime. Then I go and honestly try to derive it starting from this theory. But at least I know what I should aim. I have an idea of what the result should be. So this can be a very important guide. It can give you many hints on how to understand how to develop more powerful techniques for dealing with quantum field theory and string theory. And let me finish by giving you an example of one such hint that we would get. One such hint, so let's consider an example of one such hint that we would get. Before, did someone check this? Is this true? No? Even with this? Strange. Okay. Okay. So here is an example of how string theory can hint and can guide you a little bit. So we have seen, but I want to emphasize, is there any questions so far? Now we're changing, yeah.
So Here's are probably ruled out by this, right?
Free conformal field
Like on the
theories.
boundary.
Yeah. So it's a good example. Do we know dualities where the gauge theory or the CFT is very, very simple, like free theory? Indeed, there are proposals for dualities where you just have a bunch of free bosons. But then what happens? If you have a bunch of free bosons, what's the intuition if they are free or almost free from Feynman diagrams? You just have a bunch of propagators, but these propagators are almost not attached to each other because the theory is free. So the intuition is that this should correspond some tensionless string, some string which vibrates a lot, which in principle means that it should be described by a very complicated bulk with lots of fields of all possible spins and so on, instead of just a bunch of massless fields. And indeed, such dualities exist, and they describe dualities between very simple gauge theories, which are ON models of free bosons and so on, and what are called Vasiliev higher spin theories, which are very complicated field theories with lots of spins that no one knows how to quantize and so on. So then it's kind of a masochist way of describing free theories, where you know how to describe the free theory, no problem, you just could consider propagators, but if you are into Sado stuff, you can go to Vasiliev and suffer a little bit. Yes?
The flow picture you drew before?
Yeah.
Maybe I can ask it after lecture if it's too sidetracking now. So I was wondering why, if the 2 points are separated, why does it force me to go like in the z direction, or what do you even mean by the curly lines there?
No, the curly lines, it is just the statement that imagine I have 2 points here in the floor which are close to each other, and I consider some Feynman diagrams, which basically means I take a point and I sum all trajectories that go from one point to the other. Of course, I expect that trajectories that go to Alpha Andromeda are not very important, right? So it's the trajectories that are close to the floor that are important. But if I study 1 point here and 1 point in the moon, trajectories closer to the sun are more important. It is just that. Further away trajectories, they matter if the points are also further separated. If they are very close, those trajectories will just average out by interference and not matter.
True though that those trajectories that are like deeper in the z direction are just gonna like interpolate between different theories, kind of like in right. If that's the direction of the RG flow, then
no, we can think in 2 ways when we think about RG flow. We can think that we have the same theory, but we consider observables at different scales, or we can think that we fix the scale and then we are flowing. So I'm thinking that I fix the theory, but I consider observables at different scales that probe different scales of the RG. Okay. So the example we want to see is the following. In n equals 4, we had a gift the other day. And this gift was this -2 factor. This -2 factor was telling us that our spin chains were integrable. Okay? Now, we could now go and do the following exercise, which is related to this. Let's take the dual of a spin chain. What is the dual of a closed spin chain? It's a closed string. As we said, we should think each spin chain is a string, right? Each operator, we said, is a string. So this is a string. So what is the similar question we want to ask? We take a string, okay, that is described, for example, we can describe it, one way of describing is some vector u for some sigma and time, where sigma is the direction here, and then it moves in time. And this u belongs to AdS5 times S5. We could focus just on the sphere and say that let a string be trivial in AdS and just move on the sphere. Okay? For example, like here we consider the subsector of just operators with scalars. It's natural to consider here for example, this guy to be just a vector where u1 square plus dot 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 plus u6 square is equal to 1, which means that this describes motion in the sphere. Okay? So I just take my string where my vector is not in flat space, but it's in the sphere. So I write some action, du square, but u is constrained to be in the sphere, instead of just du square, which would be flat strings in flat space. Free strings in flat space, right? And then I could take these equations of motion, right? So we could take the string equations of motion, right? And ask, does there exist a flat connection A depending on a complex parameter mu, right? Which would be a function, okay, this may be a bad letter. This is a spectral parameter. And this u is the field u. Does this exist? Does there exist a flat connection like we had for the Landau-Lifshitz model? Which was a function of the n of this vector n, right? Because what would this existence of this flat connection mean? This would be the counterpart of what we saw before, because the existence of such flat connection implies the existence of all this infinite tower of charges, which we think of as saying that if I have my string and some bumps on the string, and these bumps scatter with each other, they scatter in a factorized way. Do you agree? So this would be precisely the counterpart of saying that if I have my spin chain and I put my magnons here on my spin chain and I scatter these magnons, that they scatter in a factorized way. Okay? So this is what you will do in today's tutorial. You will take the action for strings in a sphere, write the equations of motion, find this flat connection, and therefore show that classical strings that move on spheres are integrable, are classically integrable. Okay? But now let's try to think a little bit of what could be the implications. So is this statement clear? But now let's think a little bit of how remarkable this is. Because then we are saying the following. I have some string sigma model, and I studied the easy regime of the string, which is this one, the classical one. Just studied the equations of motion and found that there is some integrability. There exist some charges. Then you ask, what are these charges preserved when I quantize the string? When I go to the quantum level, are these charges preserved, or will I get anomalies and so on, and integrability could very well be destroyed at the quantum level? Indeed, it happens a lot. I'm not just being picky. I mean, it does happen. There are models that are integrable at the classical level, and at the quantum level, they are not. One example is, for example, Landau-Lifshitz at spin s. I told you that only for spin 1/2, the Hamiltonian was integrable. For general spin, it was not. But at the classical level, all these Landau-Lifshitz for any spin look like integrable theories. So there are many models that are integrable at the classical level, and as you quantize, you lose this integrability. But what do we know here? We know that this string theory is describing classical integrable strings at the classical level. And then, if we go quantum, 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 until the super quantum strings, we found this gift. So we found that these strings are also integrable in the hardest possible regime where we have no clue how to describe them starting from the string action. Well, but then, if we are reasonable, we say it's very unnatural to expect that I start with an integrable theory, then the symmetry is broken, but then it decides to be restored when it becomes very quantum. This would be kind of insane. Why would the symmetry be broken and then restored? Right? So then the most natural thing to assume is, well, if I saw that it's integrable, but also that it's integrable in the other endpoint, then it should be integrable always. But then you are making a sharp prediction. Then you can go and tell your friends the two Feynman diagrams. You can tell, oh, do you have something to do tonight? Do you mind computing a 2-loop Feynman diagrams? Can you compute the Hamiltonian at 2 loops, please? It will take you a few hours. And you'll say, what, are you crazy? And you will tell, no, but I have a good reason. I can make a prediction. You will compute a Hamiltonian, and there will be a bunch of coefficients of your Hamiltonian, and you will not get random numbers. You will get whatever numbers you will need to get for the theory to be integrable. It will look like a miracle. And then you can do 3 loops and find a longer range Hamiltonian, and it will not be a random Hamiltonian. You will find one that will be integrable. So you see how powerful this is. Now we don't care about string theory, but we know what direction we should go. We know, yes, we should go and compute one more loop, find this Hamiltonian, see how to modify these bit equations, and start getting information about how the string theory is becoming more and more strongly coupled. And we have a guide. We know where should we aim. We should aim at understanding that given that we have all this integrability, we should aim at understanding how the S matrix of these magnons is corrected. Because if we know how to correct the S matrix of the magnons, we just directly write down the bit equations, which are just periodicity as the magnon goes around the chain. So just having this ADS-CFT is being an extremely powerful guide. It's telling you, yes, we should go, do a few Feynman diagrams, a few more loops, recompute the Hamiltonian, from there recompute the S matrix, see if we find some pattern, and it is telling us which observable we should look at in the gauge theory, what we should expect to see, and this is, of course, a very important hint. And indeed, people went, they started computing, generalizing the computation we did to 2 loops, 3 loops, 4 loops, and beautifully they found that exactly the spin chains we were finding of longer and longer range were still integrable in a perturbative sense, namely that if you truncate at 3 loops, you get charges that are conserved plus order lambda to the 4, I mean, plus 4 loop effects. But that's what you should ask for. So this is an example of seeing how ADS-CFT can be extremely useful in hinting where we should go. Similarly, once you do these computations and see that it works, then your friend can tell you, okay, but now please, can you do some one-loop computation on your string theory and compute this S matrix of strings at 1 loop strings from starting taking into account the vibrations of string, and you will also find that the scattering of 3 excitations on the string will factorize. And indeed, people went and they computed the scattering of 3 excitations on the string by doing 1 loop worldsheet Feynman diagrams, and they saw that the scattering factorized. So there is this back and forth of information flow between gauge theory and strong theory that is guiding us and telling us what we should look at, what we should compute in order to make progress and close the gap and eventually get a full solution at any value of the coupling, which would in particular constitute a proof of ADS-CFT if you want. But you see, this is the kind of examples that people that start working in the field, of course, if ADS-CFT was not true, immediately I would do this computation of Feynman diagrams. If it would fail, I would be very skeptical. How could I have this duality and so on? And conversely, the fact that indeed people do this computation and the coefficients are straight on exactly what the string intuition would predict, tell you that, okay, it's very, very unlikely. How could it be wrong and still be giving exactly what I expect and matching exactly my intuition that is coming out of these cartoons. Very good. So again, so today you will study this motion of strings in spheres and you will find this flat connection in the tutorial. And we continue tomorrow. Thank you.